So hello everyone and welcome to this next lecture in the DC to DC lecture series, and I will continue with simulating the ZETA converter. So in the last lecture where we had left off with the ZETA converter where we were analyzing the waveforms. We had plotted the waveforms of the inductor currents, the output voltage and the capacitor voltage. In this lecture we will continue with this and try to analyze some other waveforms as well as explain the concept of why the capacitor voltage is equal to the output voltage. But as always, before I start the lecture, a little bit of brief background that if you are interested in these kind of video lectures, but you would like something a little more comprehensive, then I do have full-length online courses on the MOOC website Udemy that you can enroll for. So this is my latest course, which is Simulation of Magnetics for Power Electronics using Python. In this, I use Python and Python Power Electronics to simulate transformers for power electronic applications. So in this I talk about the basics of magnetism, I talk about the basic concepts of how you can simulate an inductor, a coupled inductor and a transformer, and I have the case of a flyback converter in which I have a high frequency transformer. And if you are interested more on signal processing and the control side, then I have another course called Basics of Digital Signal Processing for Power Engineers, in which I design filters using Python. Specifically, I use the signal package in the SciPy or NumPy packages come with Python, and I have one case study where I design a low pass filter and a band and a notch filter. And my oldest course, or rather the first course that I created, was simulating power electronic circuits using Python, in which I talk about how you can simulate circuits with Python power electronics. I talk about how you can install Python power electronics, a little bit of basic background about power electronics theory, and finally a case study of simulating a buck converter. So the links for these courses are there in the description for this video. So if you are interested in more comprehensive online courses, feel free to check out the description of this video and you can access the links. So back to the lecture. So coming back to where I was, we had plotted the capacitor voltage and we had seen the capacitor voltage and the output voltage are roughly equal. Right? Now in this, let us try to figure out why that is the case. So first thing is, let's go back to our circuit and check out what's going on. So let's say initially the system is at rest, which means everything is switched off. Capacitors are all uncharged, voltage across them is zero. Currents, inductor has no currents in them, the currents are all zero. There is no magnetic field, there is no electric field, there is nothing. The circuit is dead, right? There is no output voltage. Now, when I switch on the switch, when we turn on the switch for the first time, right? In that case, you have a path in the clockwise direction, right? And you have another path that is in this direction through voltage source, the switch and the inductor L1, and you have a larger path in this forward direction through the capacitor, through the second inductor to the output voltage, right? Now, the first path is fairly easy. When the switch is turned on, the entire voltage appears across this inductor, right? So the voltage across this inductor is equal to the input voltage. Now, about the forward path, initially the capacitor is uncharged. So when the switch is turned on, the voltage is zero. The same goes for the output voltage. Voltage is zero. So which means the entire voltage, input voltage, falls across this inductor L2. So the voltage across inductor L2 is also equal to the input voltage, right? So it seems strange, but both the inductors have the same voltage, right? Now, as the current starts flowing through, initially that's how it is, because you know the principle of an inductor, it will not allow the current through it to change instantaneously, which means as the current is zero, it will block the entire voltage and the current will gradually start increasing, right? Now, as the current through both of them start increasing, the capacitors also get charged, because as this current increases, the current through the capacitor increases, which means this capacitor is getting charged. And as the current through the inductor increases, the current is also going to flow through the capacitor. So the output capacitor is also going to get charged. So now these two capacitors are getting charged. And as you can notice, the current through them is the same, which means the voltage across these two capacitors is the same, right? Now, if you were to apply Kirchhoff's voltage law, that also adds up. For example, if you look at when the switch is turned on, this is a loop. So, as per Kirchhoff's voltage law, the sum of all the voltages in this loop will be 0, which means the voltage source, right, the input voltage plus the inductor voltage will be 0, which is why the inductor voltage is equal and opposite to this input voltage. Now, coming to the larger loop, the input voltage plus the capacitor voltage plus the inductor L2 voltage and the output capacitor voltage will also be 0. The sum of them will be 0. Which means we have seen that the inductor voltage mirrors the input voltage, right? We have seen that. Why? Because we say that as the current is 0, the entire input voltage comes across the inductor L2. As the current starts increasing, the voltage across the inductor remains the same. Why? Because both the capacitor, the decoupling capacitor, as well as the output capacitor are charging at the same rate. And these two voltages are exactly the same. Alright, these two voltages are exactly the same. And because these two voltages are exactly the same, we have these two voltages equal and opposite. And that's what is happening. Alright, now I would encourage you to measure the voltage across this inductor and across this inductor and verify that for yourself. Right? So, another thing which we can do is we can go over to our main page, edit circuit parameters, and check out the component parameters. We will ensure that the decoupling capacitor, this decoupling capacitor and the output capacitor are the same. So, for example, we say that the output capacitor is very small, right? Let's increase this. So, let me increase the output capacitor to be 500 microfarad. And the input capacitor or the decoupling capacitor is 100 microfarad. So, with this, let's go and run the simulation. So, now that we're here, we should also examine another thing which we saw was different, and that is the inductor currents. So, we see here that the current through inductor L1 is smaller than the current through inductor L2. But this is a specific case of a low duty ratio. The reason is because the duty ratio is low, the current through the inductor L1 is going to be lower because it is turned on for a lesser amount of time. And as you see from the circuit diagram, the lesser the amount of time the switch is turned on, the inductor current will have a lower magnitude for the simple reason that this is directly fed by the input. On the other hand, the inductor L2 is in this larger path. So therefore, even if you have a complete, or rather you have a low duty ratio, the output, that is the inductor L2, is still charged by the capacitor C1, right? And similarly, the inductor L2 will freewheel through the output capacitor when the switch is turned off, right? So therefore, this is the energy that is fed to the inductor L2 is from different sources. So anyway, now that we have this, let's go and run our simulation again. So let's plot the output voltage. And this is the output voltage. It's significantly smoother because we've chosen a bigger value. So we have a value of 0.14. So let's go and zoom in between 0.14 and 0.141. And let's do the same for here. So my X zoom will be 0.14 and 0.141. Let me plot this. So this is the output voltage. Let us zoom in between 4.5 and 5.5. And you see, actually I can zoom in even more. So let me zoom in between 5 and 5.2. Okay, that is reasonably good. The fact that it is increasing shows that it's not completely reached steady state, but that's still okay. Let us now plot the capacitor voltage for the same range. So this is the capacitor voltage, 0.14, 0.141, and let's do 5, 5.2, and plot it. And we see they are not the same, right? So let's go plot it first and let's see what we get. The reason is, one of the reasons which we could achieve that is that it is still not settled, right? So for example, you see here that this voltage is still not settled. Now, one of the reasons, of course, obvious reasons which I now realize, is it's a negative voltage, that's why we don't get it. So let me go zoom in between 0.14 and 141. And here we zoom in a negative range. So therefore what I'm going to zoom in is, I'm going to zoom in between minus 5.5 and minus 4.5. And let's plot this. So we have this and we have this. Now if we place these two together, we see that they are roughly the same, and they will not be exactly the same because of course they are two different values of capacitors, and also which is why the ripple is very different, and also of course there will be the effect of parasitic resistance and other loop elements which are changing the value of the voltage, because remember there are also drops across the parasitic resistances, right? There are parasitic resistances in the circuit and there are drops across those which we have not taken into account. So ideally they should be exactly the same, but they are not exactly the same because of those drops. But if you look, the structure is almost the same, right? It's a very, very similar structure that we look at. So the concept here is, as I said, the capacitor, that is a decoupling capacitor and the output capacitor, the voltages mirror each other. And if we measure the voltage across the inductors, we will find that they also mirror each other. It means that when the switch is turned on, the voltage across the inductors is equal to the input voltage. When the switch is turned off, the voltage across the inductors is equal to the capacitor voltage, right? So in the case of the inductor L1, the voltage will be equal to the voltage across this capacitor, and the voltage across inductor L2 will be the voltage across this capacitor, right? Because this is the freewheeling path. So this explains why we see a negative voltage across the decoupling capacitor, right? Because of this is simply the reason why the capacitor is barely being able to charge in a certain way, and it is mirroring the voltage across the output capacitor. So with this said, let us go to the next part of the simulation, that is simulating it at a higher. Let me stop the simulation first and let me run this simulation at a higher duty ratio. Let me run this simulation at 0.7. Okay. So the idea behind this running it at 0.7 is to compare how the inductor currents are with respect to each other. So let me run this simulation as always, when you run the simulation, go to the command line and check if there is an error. Since there is no error, we are good to go. So the inductor currents. Let's come over here and have a look at the inductor currents. So it will take time to settle. That's perfectly okay. Let's go have a look at the output voltage to look at how much we would normally get. And this is our output voltage. So the output voltage in this case seems to be settling at around a little more than 25 volts. Let's go and verify that. So as always, it is input voltage multiplied by the duty ratio divided by 1 minus duty ratio. So that means 12 multiplied by 0.7 divided by 1 minus 0.7. This is the formula for the output voltage in the case of a ZETA converter. And we see it is 28, right? So let's go and run this. Let's plot it again, hoping that it would have stabilized by now. And it has indeed stabilized. So you see, we can zoom in between 25 and 30. You can always skip the zoom that you don't interested in. If you don't want to zoom, that's okay. So here we have simulated. So we see we are at around 27.5. And as always, that 0.5 volts can be accounted for as a drop across the parasitic resistance. We have parasitic resistance all over our circuit. We have parasitic resistance for the inductors, for the capacitors, for everything. So these parasitic resistances will account for around 0.5 volts of drop, which is only expected. So now that we've verified output voltage, let's go and plot our inductor currents again. And now they appear to have stabilized. So let's go and plot between 0.2 and 0.201. Let's zoom in. So we could zoom in again between around 1 and 11. It would have been probably a little more convenient if we can just zoom in using our mouse, but this is unfortunately just a PNG file. So I said 1 and 11. Make sure that the magnitude of the start is less than the magnitude of the stop, and we get a much better curve. So if you compare this with the previous case, you now see that the inductor L1 current is larger than the inductor L2 current, right? And as I said, that can be explained for the simple reason that in this circuit, when the switch is turned on for a larger amount of time, the inductor L1 receives its energy directly from the input. So if the switch is turned on for a larger amount of time, the amount of energy that the inductor L1 will receive from the input is going to be larger. And that accounts obviously for the larger current, right? The inductor L2 current, on the other hand, is largely a freewheel current, right? It receives energy from the input during the turn on state. So when the switch is turned on, it does receive energy. But it's important to understand that not only is the inductor receiving energy, the capacitor as well as the output capacitor are also receiving energy, right? So the inductor receiving energy is not exclusive. It is being shared by all three of them, by the capacitor, by the output capacitor, by the decoupling capacitor, the output capacitor, and the inductor. Whereas here, the inductor L1 receives all the energy of the input, right? So this accounts now for a larger current in the inductor L1 as opposed to inductor L2 when the duty ratio is larger, right? So these are some of the waveforms that we observed before, and if you want, we can always just do one last check. We can just plot the capacitor voltage as well. just to compare that the capacitor voltage is still equal to the output voltage but in a negative sense. And you see that is exactly the case. We saw that the output voltage is around 28 volts, the capacitor voltage is around minus 28 volts, right? So this is only expected, right? This is only expected. So now that we've arrived at this, what we can do is I would like to stop this lecture now as we have examined a few waveforms. In the next lecture, we will wind up this converter with an open loop simulation where I will modify the duty ratio from 0 all the way to 0.8 and check out how the output voltage behaves with increasing duty ratio. So this is just as a kind of a dry run if you want to insert a PI controller within this simulation to be able to regulate the output, or rather regulate the duty ratio, right? Because the open loop control merely varies the duty ratio by some random manner, but in reality you would need a PI controller that measures the output voltage and regulates the duty ratio. So as before, if you have any doubts about this lecture or about this converter or about anything else, feel free to post in the Q&A forum, or not the Q&A forum, since this is a YouTube lecture. Feel free to post in the comments or message me on social media or email me, whichever is your preference, and I will try my best to help you out. Or I will see you in the next lecture, which will be next week, where we will do the open loop simulation of the ZETA converter. And with that, we will wind up the ZETA converter series. So, thank you so much for watching and see you soon. Goodbye for now.